Alright, welcome back folks. Today we'll be studying the properties of vector fields, and these properties are directly derived from the definition itself. Okay, so just a quick note before I proceed with this. All of these properties, including the properties of fields, they're not exactly anything special. They are just things you have been using for a while now. They are things you understand intuitively, but I just added some mathematical logic to those things. So, in general, whenever you're using fields or I'm sorry, this should be vector spaces or vector spaces in any scenario, then whatever your whatever stuff you have used with real numbers or matrices before, they most of them will apply in this as well. It's just that many of the properties have been taken for granted, and right now I'm just giving you mathematical proofs. Alright, so firstly, the zero vector, that is the additive identity, has to be unique. Okay, that's just like the fields. The zero over there was also unique. Same proof as before. There will be two zero vectors, 0 and 0 dash, and 0 and 0 plus 0 dash will actually be 0. Why? Because 0 dash is an additive identity. But similarly, this expression will also evaluate to 0 dash because 0 is also an additive identity. So from 1 and 2, I can say that 0 and 0 dash are equal. Sorry about that. Secondly, for any u vector, the additive inverse is unique. Well, again the same proof as before. So even in the fields, we proved that the additive inverse was unique. So now do you understand why I told you to not just memorize the proofs? In fact, go through the algebra carefully. It will be useful. So here, although this is not the addition for scalars, which are fields, this is vector addition, but nevertheless the logic or the concept that we use remains the same. So suppose there are u1 and u2, which are both additive inverses of the vector u. Those two, when added to u, will be 0. That's what this step is about. Now u1 can be written as a sum of u1 and 0. Why? Because that's the definition of 0. It will result in itself. Now this 0 over here can be written as u plus u2, because that's what this equation is about. U plus u2 is 0 because u2 happens to be the additive inverse of u. By associativity, I can shift the parentheses over here. That's what this step is about. Now this expression inside the parentheses, it evaluates to 0. That's from equation 1. And so u1, which has been the LHS all this time, is equal to 0 plus u2, which is u2. And so if we have two additive inverses, then obviously they have to be equal. That's what we have proved here. And hence the minus u, that is the additive inverse of any vector u, is unique. Okay, now the third and fourth properties, they are also pretty simple to prove. Again, the logic follows from the proof that we did in fields only. It's not that big of a rocket science. So look at this. The scalar 0 times any vector u happens to be the 0 vector. So 0 times u can be written as 0 plus 0 times u. The 0 can be decomposed into 0 and 0. Well, that's what the additive identity in f is all about. Now by distributivity, I can split this into 0 times u plus 0 times u. Not a problem. And so let's cut this. We can cut this. So that's basically adding the additive inverse of whatever this is. When I add it over here, that will result in a 0 vector, and right here that will result in 0 times u, and hence 0 times u happens to be the 0 vector. Now similarly, a, for any scalar a times the 0 vector is also the 0 vector. Okay, so that's also not a problem. We use the same logic as before. So instead I have decomposed 0, the scalar 0, into the sum of 0 and 0, which are two scalars. Here I will decompose the 0 vector into the sum of 0 and 0 vector. Now again, distributivity, add the additive inverse on both sides. That will give me a times the 0 vector is 0. Similarly, minus 1 times u happens to be the additive inverse of u. Why isn't that surprising? So let's do that. Now again, in the fields, that's where I also did this, that minus 1 times uh, a number is the additive inverse of that number. So it worked there. Similarly over here, 1 plus minus 1 is 0. That's the property of the field. And now here, if I multiply u on both sides, the RHS will evaluate to the 0 vector. That's what we proved before. And now, if I distribute this, then that will become u times 1, again u, and then u times minus 1. That is 0. So by the definition, shouldn't u times minus 1 be the additive inverse of u? Well, obviously it should. And since the additive inverse is also unique, that's what we proved before. Minus 1 times u is minus u. Simple as that. So yeah, this might seem confusing, since minus 1 times something is minus of that. Well, again, that's where you have just been taking that property for granted. This is how it's actually proved. So it works in fields, it works in vector spaces as well. Okay, with that I conclude this lecture. In the next one, I'll provide few nice examples of vector spaces, and there we'll be looking at our all favorite matrices, polynomials, all those things. Okay, until then, stay tuned. See you next time.